Good day and welcome to the session on reinforcement learning. My name is Blaauw. I'm with PwC and currently heading the Applied AI and Machine Learning Research and Development Initiatives in the actuarial practice in Johannesburg. Please note that any opinions expressed here is that of the presenter, not necessarily that of PwC. And also note that anything said is not to be taken as investment advice. Good, so looking forward to the session. Okay, so RL is really starting to take off. I'm sure you guys must have followed Elon Musk announcement the other day that Tesla's autopilot will achieve fully autonomous level 5 capability this year, which is really awesome. And RL is also really starting to take up in other fields of business, as we'll see later. So what we'll be covering is these items here. We're looking at reinforcement learning as a type of machine learning and how it differs from other types of machine learning, the RL system and its components, a brief look at RL algorithms, identify some application areas in business, and then look a bit more detailed in RL application investment portfolio optimization. And then wrapping up with some issues in RL model risk management, as well as some ideas on how RL can be used in the AI strategy of the firm. Okay, now reinforcement learning is really a type of machine learning. I mean, we're all familiar with supervised learning and unsupervised learning. So the third category of machine learning is reinforcement learning. So how does reinforcement learning differ? Well, supervised learning, you have a model or an agent that is using label data to try and make a prediction in classification or regression. And typically the goal is there to generalize. So you try to get an agent to generalize on unseen data, and that then can provide accurate predictions. Unsupervised learning, or so-called representation learning, the task of the agent is really to learn from unlabeled data, to compress, to provide a compression for better understanding of high dimensionality data. Reinforcement learning, the task of the agent is to learn through trial or error to perform an action. So supervised and unsupervised learning really is kind of perception tasks being performed there. It's typically a human in a loop, and it's really a type of augmented intelligence where the agent is providing some clustering or classification, which has input into some human action. However, in the reinforcement learning case, the agent performs an action task. It's typically not a human in a loop, so it's a fully autonomous process. Now, deep learning, as we all know, is a very powerful techniques using neural networks, and it can be applied to solve machine learning tasks in all of these three branches. However, what one does find is that for reinforcement learning, deep learning, neural networks are typically the go-to method. The other tree-based algorithms and kernel-based algorithms that typically work well for supervised learning and unsupervised learning just is not powerful enough for reinforcement learning. So reinforcement learning is purely starting off typically with neural networks and building up from there. Okay, the reinforcement learning system. Now, unlike many other areas of machine learning, in reinforcement learning, you typically don't have one model. You have multiple models, so it's common to talk about an RL system instead of an RL model. There are many components in an RL system, which we will uncover a bit later, but the two main ones are really the agent and the environment. Now, the agent is really the solution. That's the engine that actually can make decisions through various applying various complex techniques to come up with the best decision on the uncertainty. The environment is really the representation of the problem. And the agent interacts with the environment influences the agent, and so the whole process goes through that loop. Now, how the environment reacts to certain actions of the agent is defined by a model. And that model of the environment can either be known by the agent, in so-called model-based reinforcement learning. In this case, you actually need to build a model representing the environment. So it becomes pretty complex, and it can also be error-prone. However, there's also another approach where the agent does not know the model at all. It actually makes decisions with incomplete information, the so-called model-free RL, where the agent actually uses trial and error to make its decisions. Or you can get a kind of hybrid approach between the two, where the agent has some knowledge of the environment and no knowledge at all, but as it goes along and experimenting through trial and error, it can actually build up a model of the environment. Okay, so let's look at the RL system components in a little bit more detail, and in particular how the agent behaves. Now, as we said just now, you have environment, you have agent. Now, the environment is typically described by a lot of variables. And one of the key challenges in reinforcement learning is to actually collect sufficient data and define enough variables so that the environment can be described in a very accurate way for the agent to take its actions from. So in a portfolio management context, which we will look at a bit later, the environment could be, share prices, it could be economic indicators like interest rates, it could be economic news, etc., etc. So it's typically a large amount of data that has to be collected about that environment. Another key feature is that environment obviously transition from one state to the next. So that's just a change in all of these variables that describe the environment. And typically there's also a state transition model, which is a model that can estimate the probabilities of the environment moving from one state to the next. And the share price scenario, when the share price is going to go up and can go down, so there's probabilities that can be attached to that, and the environment typically has a model that also can then model those transition probabilities. Now, at every iteration or change in the environment will then make available to the agent a new state. And also a reward that was based on the agent's previous action. Right, so in a portfolio context, if the agent has actually bought some shares, and the price has gone up, and that's a reward that will, on the next change, iteration of an environment, will also be made available to the agent. Now, the agent, of course, now has to determine the best action from the environment and the reward it's received, and basically it does this through optimization of a so-called value function that tries to take the best action for possible changes in the environment, right? And then the agent would, of course, once it's taken that action, that would impact or influence again on the environment, and so the loop continues. So the agent's goal is really to maximize the overall reward it receives, okay? However, in many of these type of RL problems, the reward is not immediate. Even in a game, we play chess or whatever, you might take the opponent's piece on the next move, but that's not the right move for the goal you want to achieve at the end of the game. And the same, most problems are like that. So the agent always has to trade off exploration versus exploitation. So what do we mean by that? So either the agent can exploit what he already has experienced, or it can actually explore first and then select an action that doesn't have a best immediate outcome, but will have a better longer-term outcome. So this exploration versus exploitation trade-off is a very key part of RL algorithm. And when you build a RL model, it's typically there's a parameter called epsilon greedy, which you can set to control this kind of exploration versus exploitation. In this session, we'll be looking briefly at some of the more popular recent RL algorithms. Of course, a large and technical topic, but which is outside of the scope of the session. But Q-learning has become a very popular class of RL algorithms. It's a so-called model-free algorithm, where the agent knows nothing about the state transition and reward possibilities of actions in the environment. It discovers this through trial and error. Now, the Q comes from the Q function, or the so-called beta function, which is a very key component of RL algorithm capability, because that beta function really determines the best action to perform in a given state of the environment. Now, the basic idea of Q-learning then is to approximate the value of these actions for samples observed during interaction with the environment. And this process is called temporal difference learning, so-called TD. So the agent would make an estimate of an action or the value of an action, then take certain actions to trial and error, get new information, then refine or update that estimate, and that determines then what the next action would be, best action would be, and so the process continues. Now DQN uses deep Q-learning for approximating the value function, and DQN has been very popular and successful in high-dimensional problem spaces where the action space is discrete, like in computer games, Atari games, and these type of games which RL agents has been trying to play against. DKN has been very successful in that environment. However, it's not so suitable for continuous action spaces. So DDPG, or Deep Deterministic Policy Gradient, has been an enhancement on DKN for continuous action spaces, which you typically find in business, and also like the portfolio investment problem, which we'll talk about later. A further enhancement of DQN is the so-called actor critique architecture, where one agent, the actor, is used to decide on the best action in a specific state, and then another agent, the critique, is used for evaluating the policy function estimated by the actor, according to this TD error. Now, multi-agent DDPG is a recent enhancement to the DDPG architecture, and it operates through multiple actors coordinated through a single controlling critic. Now, this is a recent development, but based on earlier results, it looks really exciting. This MADDPG seems like it would significantly enhance the capabilities of DDPG algorithms which we currently have. Now, a problem that you have not so much in RL, but also in neural networks in general, is the so-called flat surface problem, where there's a zero gradient solution space and no gradient to work with, so the optimization algorithm cannot really come up with a solution. So, in RL, this is a very big problem, because if the agent cannot, if there's no gradient to work with, the agent won't move in any direction and it will get stuck, and it could be quite catastrophic. And all of deep learning algorithms suffer from this problem, and also all of the DKN algorithms. Now, genetic algorithms is also an alternative to neural networks to solve RL problems, and genetic algorithms can overcome this flat surface problem. They're relatively simple to use, and it's really an algorithm to look at as an alternative to deep learning. They're quite simple and normally give good results. Okay, so enough of the technical algorithm stuff now. Let's switch gears a bit and start looking at exciting area of RL application. Now, RL systems and solutions can really be used for any problem setting that requires decision making on uncertainty. And in businesses, there are many of those type of problems. However, probably the most suitable one is any type of resource management problem. We have to do some kind of resource allocation, scheduling, like in transportation, and so on. So all of these type of problems are suitable for RL. What is required though is that that the problem needs to be reformulated and framed as a RL type problem, which requires that you need to define the environment, what actions, state transitions of the environment, the reward signal, and so on. And once that's been done, RL can be used as a very effective alternative for current optimization problems that's running out, solutions that's running out there in resource management. A very interesting recent development is the application of RL in online sales recommender engines, where RL is showing some very good promise, outperforming other ML algorithms such as collaborative filtering, etc., which is very exciting. But we also see as RL some use cases starting to merge of using RL in debt collections, where some fintech crowd in Germany has done some very good work in using constraint reinforcement learning algorithms to optimize debt collections, and really showing that these algorithms can outperform debt collection scorecards and other traditional techniques by really a large margin. However, the most suitable RL application, and no doubt, is in financial services, certainly is in the field of trading and investment management. Now, here you have some very complex decisions that need to be taken in asset allocation, trading strategies, order execution, etc., in an environment with a large amount of uncertainty, a big data environment which continuously changes, and really challenging to take those type of decisions. So the key decision in that environment is one of investment portfolio optimization, which has become really challenging. Now, the objective of investment portfolio optimization is to maximize returns while minimizing risk, and that's done by finding a so-called the optimum weight or optimum portfolio allocation of assets to achieve that objectives. And we'll look at these techniques to doing so in a bit more detail in the next slide. Okay, so let's look at investment portfolio optimization techniques in a bit more detail. There's many of these techniques have been applied over the years, starting with traditional techniques, have been around for a long time. And then in the last 10 years or so, you've started seeing supervised, unsupervised machine learning techniques also being applied to this problem. And more recently, last 3 to 4 years or so, also RL algorithms to address this problem. Now, the traditional approach is really just using statistical techniques, volatility and correlations to construct a so-called mean variance portfolio with some optimization technique. And the issues and problems with this type of techniques is that really it depends on these statistical assumptions of normality and constant volatility and constant correlation and so on, which don't always hold in the market, because markets are dynamic and they change. And as soon as those assumptions are invalidated, then the portfolio weights that's calculated are not valid anymore. So it's a static approach, and it's got a lot of limitations. In supervised machine learning, of course, one application of supervised machine learning is forecasting using sequence-to-sequence algorithms like LSTM and recurrent neural networks. And one approach has been to start using these techniques to forecast asset prices and then allocate the weights accordingly. However, the issues there is, of course, the forecasting accuracy. And although LSTM and these kind of techniques are starting to show good promise and sort of fairly accurate forecasts over short term, up to 3 months or so, over longer term periods, they start to break down in terms of accuracy. And of course, you get these regime shifts in the market, which means those forecasts are not then valid anymore. So this approach is also not very effective. Unsupervised machine learning has also been used, and two type of approaches there. Dimensionality reduction algorithms has been used, kernel PCA and so on, to construct uncorrelated portfolios, the so-called eigenportfolios, which then means that you get portfolios that's not correlated, which diversify the risk away. And another approach there is to use hierarchical clustering techniques to allocate risk recursively, the so-called hierarchical risk parity approach. Now, issues with these techniques is that they don't scale well, and they also suffer from static, to a static approach, because you allocate these weights in a structured portfolio at a certain point in time, but as soon as the dynamics of the market change and the structure of the market change, it's not valid anymore. Now, RL has also been used, and the model-free approach in RL has been, that we described earlier, has been particularly popular. And the RL approach is to optimize a policy or a sequence of actions that the agent needs to take in a similar environment that is experienced in the past to optimize the portfolio weights. And these approaches have been working very well. We'll see soon some results. Challenge there, of course, is sufficient data, always as with RL, but as it turns out, that's not too much of a problem in financial markets. Okay, so let's look at RL performance then in portfolio optimization versus these other type of techniques. So first of all, this is work, case studies that was done by a crowd called Neuron Lab. We in our own firm have done similar studies, not to the same extent, and our own findings in this space corroborates what we see here. And there's also many other academic papers and other case studies starting to emerge that sort of corroborate the kind of findings that we've seen in this study. But what was done here is to actually train the RL algorithm to maximize Sharpe ratio. Sharpe ratio is combined risk and return, and the higher the Sharpe ratio, the better, and compare that against a benchmark, and that's what you see at the top. The reinforcement learning algorithms start to learn, not doing so well at the beginning, but as it's starting to learn the environment, understanding it better, it's consistently improving its performance using a DDPG type algorithm, which learns through trial and error. At the bottom here, you see the results of alternative techniques that we just described in the previous slide. So the mean variance approach, a minimal variance here, not performing very well against a benchmark of a Sharpe ratio of 0.22. The PCA or eigenvalue portfolio type approach not doing too badly, 0.26, hierarchical risk parity, negative. Forecasting also not performing well. And then the reinforcement learning Sharpe ratio 0.46, which is really kind of phenomenal. It's about 100% improvement on the benchmark, which is really, really very good. Right, now RL systems have a lot of model risk, like all machine learning and AI solutions, which need to be really controlled very well. So some of those key risks are really complexity, and really this complexity is related to many interacting models. You also have complexity in many other machine learning models, but not many of them have this kind of many interacting models that creates additional layer of complexity that creates some risk and need to be controlled. Another key risk is this also called reward signal fit for purpose. It is very difficult to measure whether your reward signal is really the right one, because the agent can only be measured on its performance at the end of the episode after it's taken all its decisions, and not after any immediate decisions. So that risk needs to be effectively controlled, else the system will not be effective. Robustness, so-called overfitting risk, is also a key problem with reinforcement learning, so that the agent performs well on when you test it, but as soon as you apply it to data it's not seen, it starts to fall over and not performing that well. Transparency, black box issue is always a big issue with machine learning and AI models. Also in reinforcement learning, you need to understand how the agent derives its decisions, so if something goes wrong, that we can fix it and the model can be trusted. Of course, bias is also a problem, like in other machine learning algorithms, where the model could actually magnify bias in the data. So how do we mitigate this? Well, first of all, unbiased data sampling. I mean, that's really key, that you sample sufficient data over a large history that include all types of events that the agent can account for, can encounter in this decision making, and there's no bias in that sampling. Exhaustive training episodes need to be constructed, as I said, across that to show the agent can learn very extensively. This complexity of interacting models need to be tested very well. You need to identify and evaluate many alternative algorithms to address the so-called reward signal not fit for purpose problem. Hyperparameters need to be tested for sensitivity to understand where they're going to start breaking down and then address them. Some of these interpretability algorithms like Shap and Lime can be applied to transparency, to unpack the decision reasons for decisions. However, they're still not mature enough to be applied very effectively in reinforcement learning algorithms, so there's some further work that needs to be done there to get these algorithms to be more effective. Likewise, for bias mitigation algorithms, there are quite a few of these algorithms out there already that can be applied to supervised and unsupervised machine learning problems, but they're still not mature enough for the complexity of reinforcement learning algorithms. So we're going to have to wait some bit more there to get them to a stage where they become effectively. But having said that, interpretability and bias mitigation algorithms are evolving also very fast, and we soon should be able to see them at mature enough state to effectively address this transparency and bias issue. Right, so RL is evolving really fast. These algorithms are getting really very sophisticated. The multi-agent RL systems are starting to be used, further increasing the capabilities of these systems. Quantum computing is on the horizon, which will no doubt increase the capabilities of these type of algorithms and making them suitable for more wider range of applications. So RL's really got the ability to also then enhance existing data science. Many machine learning problems currently can be replaced by more effective RL algorithms. And of course there's RPA, which the second generation of RPA will all have cognitive type capabilities, and those can only be solved with reinforcement learning algorithms. So it's really important that companies start to take note of reinforcement learning and start including that in their AI strategies, identifying use cases, the kind of investment they're prepared to make and what kind of returns they need, and then to start really a process of connecting the data, experimenting with algorithms, and sort of building test systems and prototype systems to achieve kind of algorithm excellence in that space. There's really, it's an investment that needs to be made. There's a lot of complexity, but the reward is actually quite substantial. And you're then on a very, very powerful AI readiness for feature enhancements and those algorithms. However, reinforcement learning model risk is also very critical, and that needs to be managed and controlled from the outset with the right type of techniques and tools. Right, by way of concluding then, as we've seen, RL is really a powerful tool that can be used in many business applications and can enhance business value significantly compared to other machine learning algorithms, as we've seen in the portfolio investment case study. RL is complex. It will require a lot of effort and experimentation to get good results, but it's all worth the effort. Of course, RL is risk involved, but there are techniques and tools to address this kind of risk, and those risks can be managed effectively. So it's a really exciting area. The closest AI is to artificial general intelligence at this point in time, which is the Holy Grail. I trust I've whetted your appetite for RL, and looking forward to your questions.